Okay, there we go.
Right. So good evening, everyone. My name is Parishman Low. We, Lexicon Lunar Extraction in Closed Environment, would like to present our project. Next slide, please. So this is our team. We are a bunch of motivated aerospace and space engineers, including a molecular biologist. Next slide, please. So I'm going to walk you through today's agenda, starting with the problem statement, then the motivation behind the project, then a solution that we propose, and last but not least, the timeline to manufacture our system. Next slide, please. So our project work is motivated by a project from MIT called Hydration Project. So what's the problem when we want to extract water on Moon? So water extraction on Moon is a difficult process because it creates huge amount of dust, which cause a huge a threat to engineered system. And what's the motivation behind our project? We would like to excavate water near to habitat, collect dust for future uses to extract minerals, and we would like to use dust to feed the system. We would like to avoid waste of solid water mixed with regolith and collect lunar regolith for study purposes. Next slide, please. And now I'll pass the mic to my colleague, Vahid.
Thank you, Parishman. And now let me go through the design of the mission. We're proposing a dome-like structure that contain the drill, which extracting the water, as you can see in the top right figure. This dome-like structure is going to isolate the dust created by the drilling from the human habitat. We also proposing a pressurizing system that makes to collect the dust created by this drill. As you can see, the schematic of this pressurizing in the bottom right figure. Next slide, please. So at the very beginning, we faced challenges. Now you can see some of those problems and the solutions. So as an example, we had to decide how we want to pressurize the chamber and which material we are using as a gas for this chamber. And in the following slides, I can bring you to the detail of these problems and the answers. Next, please. Now let's focus on the structure of the dome. So we are having a pressurized chamber. As you can see in the middle picture, we introduced a lower part for this dome to just let the pressure doesn't detach the system from the ground. And also we are using a superlative material like a graphene coated aerogel below this lower part to just let this material get the form of the ground to make the system be more isolated. Moreover, for the structure of the dome, we are using a 3D printing method with the aluminum alloy. So for the test, we are using this method, but in the test, we are checking if we can use some origami full level structures or not. Next, please. Now let me explain the design of the mission. Now, as you can see in the bottom left figure, at the middle, we have the drill, which extracts water. And as you can see, the water can be stored in different tanks in the left. Moreover, we have the compressor that pushes the gas toward the area that we are drilling. So this pressurizing gas makes the dust spread in the system, spread in the dome. And because of the difference in the pressure created by this compressor, the dust carried by the gas naturally goes through the filter in the valve in the bottom part of the dome. As the dust and gas passes through the filter, we are using some porous capsules in the different levels of the holes. So we are considering 3 different porous capsules with the different size of the holes, which all are in the order of micrometers. So that the dust collected in these capsules and the gases passes through the filter and can be stored in the helium tank, which can be used later for the compressing again. As a very first assumption, we just assume to have a difference pressure of about 100 Pascal. Actually, we selected this 100 Pascal to because since this dome structure is not attached with the ground with some some screws or something like this. We have to be sure that this pressure inside the capsule doesn't detach the system. So we have a upper bound for the pressure in the capsule, in the dome. So as a very first assumption, we use this 100 Pascal difference between the compressor and in the dome and the pipes. And for this 100 Pascal, we calculated the pipes, which will be in the order of 1 centimeter of the diameter. And we also calculated the mass flow rate. And also we proposed some kind of compressors that can be used for the test on the ground. You can find them in the report that we gave you. For the gas, we selected the helium. We had some reasons, but the important thing is that since we are not actively thermally control this dome, and since the helium is not and since the boiling temperature of the helium is lower than the temperature of the moon at the habitat site, the phase of the helium would be always in the gases. And in the top right figure, you can see the structure that we propose for the filters. The point is that since after each circulation of this gas through this dome, the dust collected in the filters in just one of those capsules that you can see in the top right. And after each time, the capsule is rotating and another clean capsule will be used to collect the dust. Actually, this system is already developed for other rover missions in the moon, on the Mars. Next, please.
Right, so how can we use water and the minerals extracted? So for lunar basalt, the minerals can be used for life support systems, and they also can be used for raw material for 3D printing. As for the metal oxide, we can obtain them from electrolysis, and they can be used for plant growth. We also can generate helium-3 for space fuel. Next slide, please. So this is our budget. So it's divided, the budget, we have the budget for building the components and as well building the system for testing. So the total budget is approximately 3,000 euros plus 30% contingency. Just a side note that the testing of our system is not, for lunar condition, is not necessary. Therefore, the budget for building the testing system is not necessary. Next slide, please. So coming to the feasibility of our project, the size of the dome can be variable. It's easy to find the materials to manufacture our system. We can perform 3D printing testing on site, and it's easy to test using just optical sensors and barometer. We can test it as many times as we want, and we can sample the dust. Next slide, please. This is the timeline of manufacturing our system as well as testing. So we first select the size of the dome, including the size of the pipes and compressor as well, which takes approximately 2 weeks. Then we start manufacturing the structure of the dome using 3D printing and constructing filtering capsule, taking approximately 2 to 5 months. Then we assemble the dome and the pressurization system, taking 2 to 5 months again. Then we integrate the pressurization system with the dome together, taking 1 to 2 months. And last but not least, we test the system. Next, please. And this would be our partners, including our partners would be ESA's European Space Agency, EuroMoonMars, Craft Cloud for 3D printing, and MIT. Next, please. Thank you for your question. Thank you for your attention, and we're ready to answer. Me and my colleagues are ready to answer your questions.
All right, great job. So at this time, we will open up the floor for questions from the mentors first, followed by, of course, the participants. So do any of the mentors have a question?
I don't, because I was the mentor, so I don't have any questions, but I just wanted to say congratulations on your presentation. It was really great. Thank you.
Thank you so much.
Thank you so much.
Thank you.
Yes, I have a question. Well, congratulations. I think it's really interesting also that you were inspired by one of the experiments that we already have within Asclepios. I was wondering, so is this system, I know hydration was meant more for Mars exploration at the beginning, but that it could be useful for Moon exploration. Do you think your system could be adapted to both locations as well?
I can answer your question.
Mm-hmm.
Yes, you're right. I mean, the difference is just because we also check the composition of the soil on the moon. Of course, the volume of the water is higher in the North Pole, for example, of the moon with respect to the Mars. Yeah, I mean, the only difference is that, as we said previously in the slides, actually this dome is going to be adapted by the drill. So if we are and in our design we just said that, okay, for a baseline we are using this drill. So if we want to use another drill with the different dimensions, we can just adapt the dimensions of the dome with respect to that drill. And since the design of the drill was not our focus, so we are just adapting ourselves with the proposed drill actually.
Okay, perfect. Thank you.
Sure.
Okay, I have a quick question. How do you propose that you will change the filters? And do you have any idea how often the filters would need to be changed? Because they become clogged relatively easily. Is there any way that you plan to create your own filters later that can be cleaned somehow? Or how do you plan to handle the filters is my general question.
To just avoid having this cleaning of the capsules, actually the system is proposed to just avoid this cleaning. And as there's your question about the frequency of changing, actually it depends on the dust created by the drill. And since we have no idea about, I mean, the amount of the dust, so we just said that, okay, I mean, we have this system, and as I don't know if we had this in the slides, that we are proposing some sensors for barometer and the optical sensors. Actually, we are using this optical sensor to check the opacity of the environment inside the dome, to check when exactly for example, the density of the dust will be going above some predefined value. I mean, it means that the system should work. And since I think the size of this capsule is not that large, after each, because I mean, the point is that this compressor is not working all the time. I mean, whenever we see that the density of the dust in the dome is going above some predefined things, we start the fresh compressor, and after falling from that threshold, the system is off. And after the turning off the system, we can just change the capsule for the dust.
One small thing I want to add is that it could be a job of the habitat people, I mean for the astronauts. So they can monitor their system by using those sensors and the barometer, and also they can check that whether how much dust they have got and changing the capsule. So it could be one shot of astronauts work on the habitat.
Yeah, and also
yes.
Sorry. And also linked to this, another job could be actually providing the drill with some remote control, so that you don't need to be in situ to command the drill direction and so on, but you just need to look at some tablet, and you can monitor the station, and you can make your maneuvers with the drill if you need to change site of sampling.
Okay, wonderful. Thank you. Do we have any other questions? Okay, if not, then I propose that we try to stay on schedule. So we will take a 2-minute break and then we will start the next presentation. Thank you for your great presentation.
Thank you for
Thank you.
your
Thank you.
Thank you for
Thank
feedback.
you so much.
Thank you so much.